Hello, this is the exam 2 review for spring 2019. So these slides are going to cover the free answer portion of the exam as well as the reactions you need to know. The exam is going to be over Solomon's chapter 7 and 8. So initially on these in these slides we're going to talk it shows the reactions that you're going to need to know. So this is actually the more important of the two sides. So when you have an alkene plus KOH, or NaOH would also work. NaOH, just some sort of base, right? Remember, you're going to run. This is essentially going to be an E2 reaction, where you have the leaving group, right? And then you can go, as long as you've got CH bonds in the correct position. In this case, with a straight chain, you're fine, but you're going to go, on either side of where that where the leaving group was. Same goes with the acid catalyzed dehydration. So the acid turns this OH group into a good leaving group. OHs are generally bad, but once you add a little acid, they become good leaving groups, and then you're going to go on either side of the leaving group, as long as there's an appropriate CH there bond. The other ones are just the normal sort of adding HX across the double bond, sort of in the Markovnikov direction. The XX or XS plus water. Now I don't know if this is on here. One thing I did forget to put on here is if you have the if you have this, so HX plus peroxide, right? So the you're actually going to switch the you're going to get the anti-Markovnikov product. So in this case, it's going to go on the lower ordered side, right? So this is secondary versus tertiary. So it's going to go here, but otherwise it's going to go on the higher ordered side. So tertiary versus secondary. Now, if you add halide, so this is Br2, I2, Cl2. If you add this across, right, one's going to go on either side in the presence of water. However, the OH is going to come in and go on the higher ordered side. So for this one here, right, this is oxymercuration. So you're going to add, in this case, we're going to add water across the double bond. And so this one goes on the higher ordered, while the BH3 H2O2 goes on the lower side. Now, one of the hints is that just like this one requires peroxide, this one creates peroxide, and both of these have the main group, in this case OH, in this case Br or Cl or whatever, going on the lower ordered side. So it's an easy way to remember it. Now, for regular hydrogenation with palladium or palladium on carbon, you're going to take the double bond down to a single bond by adding H's across it. You're going to add extra H's across there, the hydrogen. Okay. So osmium tetroxide and NMO, right? So all we're going to do is just add OH's across it. So the hydrogenation is to put H's across. The osmium is going to be putting OH's across on either side. Now for for ozone, right? So we're going to be cutting these, slicing these, and we're going to turn what used to be carbon-carbon double bonds into carbon-oxygen double bonds. So for that, you're just going to slice it right like that. You could do the same thing with the permanganate, and that would make the aldehyde. But the aldehyde is also reactive with this, so it turns into an OH. Turns into the carboxylic acid here. So with sodium, or in this case, iodic acid or sodium periodate, it's really the IO4 that's the important part. Wherever you have OHs, you can slice, as long as they're pointing generally in the same direction. Okay, it's going to be the same as if you were going to do an ozone type reaction. So a nice way of cleaving a double bond would be to put in the react the NMO or osmium tetroxide with NMO, That's going to put in your OHs, and then cleave it with say sodium periodate or periodic acid, and that's going to cleave here and do essentially the same reaction as what the ozone did here. So this is where the original carbon-carbon double bond used to be. The other thing is the adding the triangles to the double bond, right? So in this case, we're going to add chlorines to it. In this case, so here it's going to be, we're going to take out the base is going to take out the hydrogen as well as one of the chlorine, and then one of the chlorines is just going to go away, and so this CCl2 is going to become the triangle. Here, the Simmons-Smith, the zinc and copper amalgam takes out the I2, and so in this case it's just the CH2 that gets added on there to make this triangle here. There's also a diazomethane that's also, but it does the exact same thing. So now for alkyne reactions, okay, they're going to be very, very similar to it. Lots of times it's just doing alkene reactions twice, and so one of these is to add KOH or sodium hydroxide, something a strong base, and then you're essentially going to do an E2 reaction twice. So like that. So one of them is going to take this hydrogen and then this this hydrogen and this halide to make this, right? Because there's a hydrogen here, right? And you're going to leave this behind. So let's say it's a bromine, and then the base is going to come in here, grab this. That's going to collapse down, kick that away to do a second one to make this. So if you want to make if you want to make a triple bond, one of the ways you can do it is just do E2 reaction twice, right there. Okay. Again, if you're going to add HX, it's just going to behave as if there's two double bonds there, right? So with that, we're going to put the X's go on the same carbon. Here again, we're going to add on either side of this. We're just going to do the reaction twice, just like with the alkene. It's just going to do alkene twice. So now with these, what's going to happen is they're going to have the same selectivity for the hydroboration and oxymercuration. Okay. Now here they're both second. In this case, they're both secondary. So it doesn't matter. You're going to get a mix of the two. There's not really any selectivity between here. But for down here with the with terminal ones, right? There's this one which is secondary, this one which is primary. Okay, and oxymercuration is going to want to put the OH here, right? Hydroboration is going to want to put the OH here. After you do that first addition, you're going to make this into a double bond, and then so you're going to get this intermediate that's not stable, and so it snaps around to form here. But remember, wherever the oxygen was, it stays where it stays put. Same thing here. You're going to end up with this intermediate, which isn't stable, and it's going to snap around to here. So this H ends up here, and this double bond there comes up to make that. Now with the alkyne reactions, again, if you do hydrogenation with palladium on carbon, you have excess hydrogen, you're just going to take this down to a single bond. You triple bond down to a single bond by adding H's across it. Now, if you want to stop it at just a double bond, again, you're going to do a very similar reaction, but you're going to poison the catalyst, either through Lindlar or adding barium sulfate to your palladium, and that's going to add hydrogens, but they're going to be added on the same side. It's a syn addition. So for that, so you're going to end up making the cis double bond. If you want to make the trans double bond, you have to use either lithium and ammonia or sodium and ammonia, right? And then this is going to make the trans. Okay. So for the ozone and the permanganate reactions, right? We're still going to get slicing. Okay, but because we started off with a triple bond, that means we have to end up with a 3 carbon oxygen bonds, and the way that we do that is to make a carboxylic acid. And so this one here, for both the permanganate and the ozone, you end up with the carboxylic acids on either end of on this carbon and this carbon of the triple bond, right, and this one. Now with the terminal ones, what's going to end up happening is you're going to make the formic acid, this, but that's going to get further oxidized to this plus water, CO2 plus water. It's going to turn into carbonic acid, which is going to turn into CO2 and water. So if you do a terminal one, you're just going to literally going to lop off, you're going to take off, you're going to cut it as normal, but it's going to the extra product that's over here is going to get is going to go away. Now this one is just for making carbon, things like carbon-carbon bonds, right? So with sodium amide, this you can take off a terminal a hydrogen that's hanging off of a triple bond, right? So that we're going to grab this, and those electrons here are going to go right there. So this bond here ends up being this lone pair here, and then you can use that to do SN2 reactions. And kick this away, and so now you've made a new carbon-carbon bond. So these electrons here became this new bond here. So this is good for building the carbon skeletons for the zynosynthesis reactions. Okay, so one thing I'm going to be those are the reactions. Okay, so now you need to know how to use them. So one of the things I want to do is we're going to have is a pick the reagent. So it's going to be, so I'm going to give you this. So what reagent is going to have you go from an alkene to halides on either side of it? Well, that's going to be the this one right here. So you're going to say, pick from the list. Okay, so here you're going to go from an alkene to adding water across here, right? So HOH, right? Stuff like that. So it's either going to be hydroboration or oxymercuration here. So for that, so this is the tertiary and this is secondary, right? So this is tertiary because there's 1, 2, 3 carbons attached. For this one, there's only 1, 2 carbons attached. So it's going on the lower ordered side. So that means it's hydroboration, which would be A. So you'll have this big list. You just got to match it up. Now you're also going to have predict the products. Okay, so this should be zinc plus a little bit of acid with that, and so here you're doing ozone. So the way that I like to do this is to sort of draw this sort of elongated. So here, right, there's hydrogens here. Right, so here's the double bond. So I'm just going to be slicing it like this, and then we're going to add oxygens on either side. So the way that you can draw this, and I would encourage it, I think it's easier to do it, is to just draw it like this. That's perfectly legal. That's your product. Now, if you want to be really fancy, 1, 2, 3, 4. You can draw it stretched out if you'd like, but if you draw it like this, that'd be fine. Now, HBr and excess HBr in the presence of an alkyne. Right, we're going to put the bromine's going to go on the higher ordered side, and we're going to do it twice. Right, so this is secondary, that's primary. So the bromine's going to go there. 1, 2, 3, 4, 5. Right, and so we're going to add it like this. So this went from 1 hydrogen, right, to 3. Right, so we had HBr across there. Now here, osmium tetroxide and NMO, right? We're going to add OHs on either side. Right? So you end up with like that. Now here, this is oxymercuration, right? Because we're dealing with mercury. So for here, and we have an alkene. An alkene. So this is, right? That's secondary. That's primary. And oxymercuration always goes on the higher ordered side, so that means that we're going to add the OH here and then the H here, right? So there's already 2 hydrogens. So we're going to add, right, so this is going to go H, 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 right, and this carbon, right, there's already an H here, H and then OH, like that. Okay. Now for this one, to form the halohydrin, right, so the first one that goes on, right, so this attacks there and then kicks that away, and we're going to want to put that first chlorine there. But then you form the carbocation there, and that's where the water comes in. So what's going to happen is the first thing that gets added is going to be this chlorine, so that goes on the lower ordered side, right? So this is tertiary versus primary, right? So we can make the tertiary carbocation, and then that means that the OH is going to end up here, right? The water is going to attack, and then the extra hydrogen is going to go away. So this is that's your product. Now you're going to have one of these reactions where you have to, but they're all essentially the same, right? So here you're adding HBr, right? Here you're adding BrBr. Here you're adding BrBr, and then HOH. Okay, so the general mechanism is the double bond is going to attack. In this case, it's going to do the polar covalent bond, but obviously in the BrBr, this is the same, so it doesn't really matter which side you do. And it's going to kick the other bromine away to leave the carbocation, and then something's going to attack. So it's either going to be Br minus, if that's around, or if water is around, that's going to attack instead. Remember, that's HOH. That's going to attack. Only if this is around. Otherwise, the bromine is going to attack and put that in there. So that's how it works. Now, with the hydride shift, okay, so I'm going to give you, this, and then I'm going to tell you what the product is here, and tell me how does it go there. Okay, so if we're going to do an acid catalyzed the dehydration, right? So the OH is going to grab a hydrogen from the hydronium ion, okay, to make this into a good leaving group. Now it's a good leaving group. That's going to go away to leave behind the carbocation. Now here, right, that's a secondary carbocation. In this case, if we move that, if we move the methyl group over, okay, now the that carbocation is tertiary, right, because it's got 1, 2, 3, much more stable. Now the water, in this case, we're doing a dehydration, so now the water can come in, and, well, in this case, it's going to be, the double bond's going to be here, right? So that means we have to, grab that hydrogen, collapse down, and we end up making the this plus HOHH, right, which reforms our catalyst. Okay, but this is the same. This is the reaction that happens with all of them. Okay, you make the leaving group's going to go away. You're leaving the carbocation. It's going to shift over, and then your base is going to come in to rip off the hydrogen. Now for design of synthesis, okay, so what you're going to want to do is sort of take a look, right? So it's always a good idea to count the carbons, make sure I'm not having to do a cleavage reaction. Just a quick check, right? 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. Okay, so we don't have to worry about any of the cleavage reactions. Okay, so how do we know how to make one of a ketone? Well, I just said you could do it with a cleavage reaction, but I said, but we already have all the carbons we need, so let's try not to have to deal with that. So the other way that we could do this, okay, and right, the other way that we could do this would be if we were to take a triple bond and either do oxymercuration or the hydroboration. Okay, that's going to end up being, it's going to put a C double bond O like that. Now, if we had the triple bond here, okay, it's secondary versus secondary, so there's no specificity, right? Because this one wants to go on the higher ordered side, and this is going to go on the lower. But if they're both secondary, there's no difference. So you're going to get a mixture of the two. But if instead you do the terminal alkyne like this, so you make the triple bond between these two carbons, now you've got secondary versus primary, right? And then we can do the specificity. So what we want to do is we want to have a triple bond right there, okay, and then run the oxymercuration, which is the HOAC, right, plus water, and then sodium borohydride. Okay, so now the question becomes, right, so we have our 6 carbons, right, and then we need a triple bond there. Well, here, these 2 carbons here are probably going to be these 2 carbons here. So what that means is we need to turn this double bond into a triple bond. Well, how do we make a triple bond? Well, we know that what we can do is do, say, BRs across there, okay, and then you just use an excess of base, right, like sodium hydroxide or KOH, doesn't matter, stuff like that. So that's going to turn, for each one of these halides, you're going to get a pi bond, okay, and since we're going between these two, we're going to make it here, okay. So how do we take a double bond and add bromines across it? Well, you just dump in bromine like that. So there's our synthesis. You're going to want to start working backwards. So how do I get this? Well, I get this by taking a triple bond, doing a hydroboration, right? That's going to make this methyl ketone here. Well, heck, how do I make that? Well, I would have to start with this. If I can't do bring an alkyne sodium amide, put that thing together. I don't have that option because I have to start with this. So going from a double bond to a triple bond, what you do is you add bromines across here and then add the strong base, and you can do this. So what I'm looking for is this here. So you have to know your reactions, be able to predict, okay, how do I make that group? So you're going to need to know the reactions both forward and backwards, because you need to be able to predict, if I make that, how do I make that functional group? You have to pull that up. Okay. Now the last thing is doing E and Z, right? So by that, so remember we're going to do, we cut the double bond like this, right? And let me do this. We'll do a black side and a blue side. Okay, and so what you end up doing, right? So we're going to look at the 2 groups hanging off of that carbon, and then the 2 groups hanging off of that carbon. Okay, and we do high-low. Okay, and so for here, right, this is CH2, right? So it's carbon, right? Only 2 bonds are shown, so it's the other 2 are hydrogen, right? So CH2, CH2. Okay, so that's a tie. Okay, so we look at the bonds, right? So this has 2 carbon-carbon, 2 carbon-hydrogen, right? 2 carbon-carbon, 2 carbon-hydrogen. So the heaviest bonds are carbon-carbon, and they both have 2, so it's a tie. So then we move out to here. So now we're gonna check out that versus that, right? So this one has, right, it's a carbon, and this is also a carbon, so that's a tie. This one has 2 carbon-carbon bonds, right, here and here. This one also has 2 carbon-carbon. Only 3 bonds are shown, so there's a hydrogen here. So there's 1 carbon-hydrogen, and then 1 carbon-oxygen. Okay, this one, however, has 2 carbon-oxygen bonds. And so the heaviest bond in this case is carbon and oxygen. This one has 2 of them. This one only has 1, so that means this is the high side. Okay, and this is the low. Now on this side, right, so here we have a carbon, so that's a tie, right? But if we look at this one, right, this one has 2 carbon-carbon bonds, and so since we only have 2, that means the other 2 have to be hydrogens, 2 carbon-hydrogen. Okay, this one here has 3 bonds shown, so there's 1 hydrogen, so there's 1 carbon-carbon bond right here, 1 carbon-hydrogen bond right there, and then 2 carbon-nitrogen bonds. Okay, so the heaviest bond here is carbon-nitrogen. Here it's carbon-carbon. Nitrogen turns out to be heavier than carbon. Okay, so this wins. And so this is, in this case, the high is up here and then the low is here. And so are the highs on the same side? Nope. We have one down and then up. And so since they are not on the same side, this ends up being an E. Okay, good luck.